Okay, it's 4. So I guess we can start. This talk is about the Scala.js compilation pipeline. My name is Tobias. Some of you might know me better under my GitHub handle here, or a Gitter. Just before I start, if there's anything which is unclear, please feel free to interrupt me anytime. I would just ask you to raise your hand so we can get your microphone, or somebody can get your microphone, or come up to the microphone just so translators can translate to me or to the Japanese speakers. So in this talk, I'm trying to demystify a bit how the Scala.js compiler actually manages to take your Scala code and create JavaScript out of it. But before we do that, let's first have a look of how the compilation pipeline actually works on the JVM. So how does Scala compile for the JVM? Let's say you write an application, and you write your application, app.scala, you feed that into the Scala compiler. The Scala compiler will create class files, and you feed these class files to the JVM, and it will run them for you. Right? It will call the main method and execute the bytecode in your class files. So far, so good. Let's say you're using a library. Oh, forgot about that. Yeah, usually these class files, you would package them in a jar in your deployment process, but fundamentally nothing really changes. The JVM just opens up your jar and gets the class files out of the jar. So let's say you use a library. Let's say we have a list type in that library, right? As an example, which is there. So the author of your library does exactly the same, right? He writes a couple of Scala files, feeds them into the compiler, packages them and packages the class files in the jar. Right? And this jar is what he publishes. Now, if you want to use that library, you just put that library and the class path of your JVM together with the jar of your application, and the JVM will link these two together at runtime, and your app can use the list type. You might see that this is actually not entirely true here, because if in this setup here right now, you write list in your app.scala, the compiler up here will essentially complain and say, list, what do you mean? I don't know no list. So you actually need to tell the compiler, hey, I intend to use this library even at runtime. Then the compiler can inspect the jar, load the library class files and see, oh, okay, list is this kind of type, it has these methods, and you can essentially check whether your usage of the list type in this library is same. And now we probably have all seen what happens if you forget to put that library in the execution class path. At runtime, the JVM will go up and tell you, hey, what do you mean list? Okay, let's fix that. In Scala.js, this looks actually very similar. Okay? We have our source code to the left. Now we run the Scala compiler, just with the Scala.js compiler plugin enabled. It just produces Scala.js IR. Scala.js IR is an intermediate representation format. It's very similar to class files. It's just what we use internally because it fits our need better. However, then instead of running this directly in a virtual machine, you feed this to the Scala.js linker, and the linker will create one single JavaScript file. Note that linking only happens once for every final application. So the library author, down here, wouldn't actually link anything. You would just publish the library, and then you could link this together once you have your final application that produces the JavaScript file, and you run that whatever way you like, in the browser, Node.js, Phantom.js. Now, from the previous slide, we see this arrow here is missing. Right? So the compiler actually doesn't know about the types in the library you're compiling. Easiest would, of course, just be to teach the Scala compiler to use these IR files. Unfortunately, the Scala compiler hasn't been made to do that, and it's relatively hard to extend it. So instead of what we do is we just emit the class files as well. The Scala compiler knows how to do that anyways. Now we have class files. Scala compiler knows how to read class files, so that's just fine. And all of this, we package it up in jars. So at this point, it looks actually pretty similar. Again, if you get rid of this arrow here, something different actually happens. At link time, the linker will realize, hey, this list type you're mentioning here in your IR from app.jar, I don't have this missing class. That actually means it won't create a JavaScript source file. So you get an earlier error. This doesn't actually happen at runtime, like on the JVM. It happens earlier. Okay, let's fix that. Okay, so this is the big picture of what I'm going to talk about. You can see here there's two main components, the Scala.js compiler and the Scala.js linker. And yeah, that's the two topics I'm going to talk about. Let's look at the compiler. These are the phases of the Scala.js compiler. Anyone been at Chris' talk about the Scalajs internals? So that might look familiar. Actually, only these three guys are really Scala.js. Everything else is just the normal phases of the Scala compiler itself. We get that for free, which is nice. So for our purposes, this actually looks much more like this. Okay. So what happens here? We have the app.scala file. We feed that into the front end. The front end does parsing, typing. In the typing, there's type inference happening there, implicit resolution, macro expansion, all kinds of niceties are happening. The front end is also the part that uses the other library to figure out whether the usage of the list type in our example is correct. The JS interop phase is mostly, that's one of the phases of the Scala.js compiler itself, is mostly here for error detection. It also prepares exports. I'm going to show you how that exactly works. The backend is the bread and butter of the Scala compiler itself, and it essentially simplifies the internal representation of the Scala code so that it is afterwards easier to emit it into JVM bytecode, as it is initially intended. Luckily for us, that also makes it easier for us to emit it to our intermediate representation. So we can leverage that, and essentially just right at the end, the path works here. And well, we just have the JVM phase emit whatever it is done anyways. And we have our JS code phase. So let's make an example. All right, we have this multi-allergy class here. It allows us to alert the user multiple times about something. It is very useful. So we use this hello factor here to actually create our messages. And then we have the multi-alert method that loops the number of times we actually requested and calls alert. That's a JavaScript method, and essentially just displays the message. You have these nice error boxes pop up. These JS export things, don't worry about them too much right now. They essentially mean that you can call this code also from the JavaScript code. You can see later on what happens. So what happens here in the front end? First of all the types are added. So we were lazy about some types, and we just added these types, so type inference happens here. Further, the for loop is desugared. So we also can see an implicit conversion here on the integer. And essentially the for loop is desugared into a for each call. Okay. Further, the string interpolation here at the bottom is also desugared. That's just how Scala internally represents string interpolation. Okay, front end. Again, nothing there actually for us. This is just what Scala C does for us. Okay. So JS interop, what happens there? One thing, we detect interoperability errors. Right? So if you do some funky stuff on facade types, if that means anything to you, we will catch it there and tell you, hey, you can't do that. There's no errors in this code, so we won't really see anything there. But we also handle exports, right? So this method here, I said is exported, so essentially means you can call it from JavaScript. So in order that later phases can properly handle that, we create this synthetic method forwarder here. We can say, hey, by the way, there's an exported method here. You can see this in the name, right? It's exported, its method, its name is multi-alert. And yeah, we will catch that in a later phase to essentially then generate the actual exported method, as we'll see later. Hello factory is unchanged because it doesn't contain anything Scala.js specific. The backend, I said, simplifies code. So simplification means it's more afterwards. But this is how this looks after the backend. Don't worry about this too much. There's just a couple of pointers. Constructors are lifted out, so we have an actual constructor method here. Then trait mixins are resolved, so we have extension methods here. So this is also stuff we don't have to take care of. And down here we have the actual representation of a repeated parameter list. Okay, good. So here the path works. We are not going to worry about how we emit class files, but JS code. So JS code is pretty different from the other phases because instead of just transforming a given tree, it actually changes it into different representations. So it's more of a translation phase, than just a transforming phase. So in order to understand this better, we're going to look at how does the Scala.js intermediate representation look, and how does it differ from what we have right now? Because we really only have to take care of that, right? Everything else is just a very trivial translation. So the intermediate representation is in type AST form. AST means abstract syntax tree. So that is just a convenient way to represent source code inside the compiler. Essentially, if you look at this piece of code, this is the abstract syntax tree of it. We see it has a block. Okay, there's okay, good. We have a value definition. That's the name x. The value, what we actually assign is the literal foo. And it just abstracts a couple of nice things. For example, whether we have a semicolon here or a new line, it doesn't matter anymore at this stage because we don't really care. So it's easier to work with that in the compiler. Typed means just that every of these nodes has a type attached to itself. So the literal there is a string, x is a string, and so on and so forth. DIR allows for complex expressions. What does that mean? It's something we're very used to in Scala. Essentially, it means that a block or an if statement or a match statement or a switch statement is an expression and not just a statement. So I'm allowed to assign a block to a left-hand side value. We'll see that's not the case in JavaScript, so we'll have to do something about that. The intermediate representation also allows JavaScript operations. So that's essentially in any value, anywhere, you can say, hey, by the way, since this is JavaScript, just call this method on it. And well, if the method is there, it's going to work, and if it's not there, it's going to blow up, just like JavaScript does. So this is obviously something that Scala has not been intended for, so we'll have to do something about that. All right, we'll see that later. Types. What types do we actually have on the abstract syntax tree? First of all, we don't have any generics, just like on the JVM. So we have type erasure, just like in the class file format. There's primitive types, integers, doubles, booleans. We can just translate them one-to-one. And there's class types. Classes, just like on the JVM. How do classes look? Just like in bytecode, we have single class inheritance, multi-interface inheritance. Right? Luckily, Scala Compiler has already taken care of all the trait mixins, so we really have interfaces don't have any method implementations anymore. They're all abstract. However, unlike JVM bytecode, the IR doesn't support overloading. Instead, you have name manager. So we'll have to also do something about that there. And we also have the JavaScript methods, the exports. Right? So in the IR, we can actually say, hey, this method here is exported. It's a JavaScript method. And we'll see how we generate these. We've already seen a glimpse of that. Okay. So these are essentially just the three things we have to take care of. The JavaScript operations, how do we generate calls to JavaScript? And how do we generate callable things from JavaScript? And I'm not going to talk about the overloading because it's essentially trivial. We just name mangle the argument types into the name of the method. Okay, so how can we call JavaScript, right? We've seen this piece of source code here, right? Where I said we call the alert method of JavaScript. So we essentially say dom.alert. Okay. So let's look at the definition of dom. DOM has this annotation that says JS native that tells the compiler, hey, this is actually JavaScript code. So all I'm giving you here is just a description of what exists in the JavaScript world, but you can assume that this exists and is there. So the compiler is not going to emit any code for that. Then we have global scope that essentially just means, hey, I'm abusing this object to say everything which is in here is actually the global scope, and we define an alert method. So when the compiler sees this call on this type, it knows, oh, actually DOM is a JavaScript type. So it's just going to emit this global thing here, meaning that's the global scope, and we call the alert method. We use we use these strings here to use the quotes to represent calls to the JavaScript world. And we use this JavaScript dot select. I mean, in JavaScript, these are called bracket select and dot select. And we use bracket select to represent calls to the outer JavaScript world. So one thing is you can see here how we use name mangling for overloading. Right? So that essentially means it's the method multi-alert that takes an int and returns a void. And the other funny thing you can see is that although we have two very similar calls here, right, dom.alert and messages.hello, essentially all the same, they actually look very different after emission, right? Global.alert, this is like the JavaScript thing, and oh yeah, actually just hello factory here and hello. This is a normal overload main mangled call. So just based on the type, essentially, we decide whether we call the JavaScript world or we call a Scala internal method. Okay, how do methods export? So these are methods that you can call from the JavaScript world on Scala classes. We've already generated this tag method here, right, in JS interop. So in the emission phase, in the JS code phase, we're going to catch this method. And well, this is just the method that forwards the call, just like before. But we also generate this exported method. So again, we use quotes here to say, oh, this is a JavaScript method. And what this does, it says, oh, well, I'm taking any, and I return an any because the JavaScript rule is untyped. It makes sure that the arguments are of the right type, and it just calls the forward. This is also a place where overloading resolution will take place. Right? We have overloading resolution for exports. So for example, if you would say, hey, I can pass in an int or a string, it would essentially check here, oh, is the argument of a type int? Okay, let me call the int overload. No, it's a string. Let me call the string overload. All right, good. So we have IR. Great. So we're halfway through the pipeline. So now we have our jars. So let's see what happens when we link. The linker looks somewhat like that. You have as input all the IR files. Now, this is very important. These are all the IR files, not just the one which are specific to your project. These are also all your libraries. Essentially all the class files you would use to run your project. First, you have the linker phase. The linker phase, it assembles and loads all the classes which are necessary. Right? So this is the phase that would tell you, hey, you're referring to this class here, but it actually doesn't exist. What's going on? Optionally, you can enable the IR checker. That's just a sanity check for your intermediate representation. This is not usually turned on because it's quite expensive, but it's very useful for debugging, because if the IR is buggy, then some phase later might blow up and you're like, what happened? The optimizer simplifies the trees. It mostly reduces code size and execution time. The refiner, there's an additional dead code elimination pass. You will see how it can happen that the optimizer removes dependencies out of the code by inlining, for example. This again reduces code size. And after the refiner, we come to the emitter. And the emitter is the phase that actually generates JavaScript code. So it's again a translation phase. Then we have JavaScript. Optionally, you can run this through the Google Closure compiler. It will just apply a couple of other optimizations to make essentially smaller code. Okay, so let's see how our example propagates through this whole thing. The linker is what we used to call the dead code elimination phase. Right? Say, okay, everything we don't need, actually don't even consider it. We realize that it's much more of an alive code inclusion phase. Because we don't even look at stuff that is dead code. We just look at all the entry points and then essentially calculate the transitive closure over the call graph. So how does this work? Here, the export annotations come again into game. You say, okay, this class is exported, therefore this class is reachable somewhere. Okay, but this class is reachable. The class is reachable, the constructor is reachable. Okay, the constructor instantiates the hello factory. All right, so the hello factory as a class is reachable. Good. Are we done? No. Actually, a class we can reach has exports. Since we can reach the class, we can reach the exports. Okay. We can reach the multi-element method. The multi-element method reaches all kinds of stuff through the for loop in the collections library. I'm not going to go into details there. The DOM-alert doesn't reach anything because that's JavaScript world. And the message hello, well, it reaches the hello method. Okay, we're done. As you can see, the hello debug down here, we didn't even look at it, and we're just automatically not including it. Just like atomic reference. We also don't include atomic reference because nothing uses that, so we just simply ignore it. Okay, good. So now we have everything loaded in memory that we actually need. Let's look at the optimizer. The optimizer is for the understanding of the pipeline not very important, but it's just still interesting to see how it can greatly reduce complexity of code. I've commented these for loops out a couple of times because they're actually pretty ugly. So the for loop in the intermediate representation looks something like this. So we have extension methods, and then range, and inclusive, and function literals, and I don't know what. Okay. The optimizer is able to turn this into a nice, neat little while loop. This has two main advantages. One, it is faster, because you don't have indirection to the lambda anymore and whatnot. Two, it is also much, much, much less code, because it doesn't need the collections library anymore. Therefore, that's why the refiner is important, because the collections library, which is used because of range and seek and for each and whatnot, well, it's gone. We can kick it out. Less code makes us happy. Okay, good. So we're again at the translation phase. So we're going to do the same again. Before we're going to look at the IR and see, hey, how does the intermediate representation differ from what JavaScript can actually give us? Again, you can see, okay, what are the things we need to change? Or still take care of, right? Okay, you see this? Intermediate representation is in an abstract syntax tree form. Well, it's actually very easy to translate abstract syntax trees, again, back to some syntax representation. Well, that's actually easy. Complex expressions. Oh, that one's actually a problem, right? Because I said that in Scala, a block can be an expression, so I can assign a block to a variable. I'm not allowed to do that in JavaScript, so we'll have to do something about that. JavaScript operations are just JavaScript operations. Types, generics, well, JavaScript doesn't have static types anyways, so that's fine. Primitive types, we can represent them with the JavaScript primitive types, right? Well, Boolean becomes Boolean, double becomes number, and so on and so forth. Class types, we can represent them by essentially prototype chain inheritance. That's a pretty common practice in JavaScript. So single class inheritance, we model through prototype chaining. Multi-interface inheritance, the interfaces don't have code in them anyway, so we just forget about them and erase them. Overloading, well, JavaScript doesn't have overloading, so we're happy we actually got rid of it way before we even reached that point. And JavaScript methods, well, we just define it. All right, so we're actually really just left with this complex expressions thing there. And that's essentially what the interface does, is what we call desugaring. Here the example unfortunately breaks down a bit because the example code I gave is not complicated enough, but this really happens in practice a lot in Scala code. So let's just look at this a bit strange norm method that takes A as an integer and B as a string, and then converts B to an integer and calculates the norm of these two values. Nobody should probably ever write a method like that, but for our example, I guess it is good enough. This more or less translates into this pseudo JavaScript code. Why do I say pseudo JavaScript code? Because you can see you have things like return this block here. That's definitely not valid. And also you have assignments to variables. You essentially assign this block here to the variable. That's also not allowed. So what we do is we push these left-hand sides into the block. We call that left-hand side push down internally in the compiler. So what essentially happens is this, right? We push the return down there. It already looks much saner. we still have the problem of this b2 variable. So we're also going to push it down there. Okay. So that's all fine, right? We just have normal assignments. Who notices the catch? Somebody might say, yep.
So curly braces aren't valid JavaScript, are they? Like that? I think that's a C-ism, isn't it?
The question was, curly braces like that are not valid JavaScript, and it's a C-ism. The curly braces are fine. Yes, however, they do not change scope. In C, they would change scope. In B2 would essentially go out of scope here. It'd be like, nah, no B2 anymore. In JavaScript, the variables are scoped to the function scope. So as long as we're careful enough to not emit two variables of the same name, when we emit the whole function, and that's easy to do because we can just generate unique names as we go, we can actually do that and it's valid JavaScript. So it's much, much, much easier for us to desugar than in a C-like language where we had to be, oh no, but hold on, now the block we have to move upwards and downwards. The nice side effect is also that these blocks actually auto-simplify themselves. Essentially, when you create a block, it just looks at its inner elements and it sees, oh, one of my inner elements is a block as well, so I'm just flattening that, essentially. Which is also something in a C-like language you couldn't do because you would essentially destroy scope. Okay. This is actually JavaScript code. Sweet. Yeah, but that means we're done. Right? You just drag that to a file, done. Okay. That's how the final code somewhat looks like. You can see these are the constructors for, this is the JavaScript-like constructor for the class. We have our loop, the hello factory, and I emitted the pretty ugly interpolation. Yes?
I'm not quite sure if it's relevant, but in Scala sometimes you shadow, let's say, a variable from an outer scope with someone from an inner scope. They have the same name, so how is this being treated in the...
There's a couple of shadowings, right? Inside the function, we generate, for local variables, we just generate unique names as we emit each individual function, right? There's shadowings, private members are shadowed, right? So if you have a subclass, and you just re-implement a private member, right, that might actually have the same name, but they shouldn't know about each other. That's the problem in JavaScript, because no private members. So we need additional name mangling there, where we essentially we use the number of superclasses that we attach onto the identifier, so we know that the identifier is unique.
You make a naming rule to cope with it. You make a naming rule of the variable, right?
Yeah, exactly.
Thanks.
Sure. Yeah, so this is JavaScript code, A to B. Yeah. These are, let's do questions first. We have quite some time. So are there any questions about that? What would you like details on? Yeah, anything.
When you go like from scope and you put the variables at the end, why do you leave the brackets in the end? Because if there is no scope in JavaScript, this is just extra characters from nothing.
Yeah, here I leave the brackets in the presentation because when I change the slide, it looks nice. In the compiler, actually, as I mentioned, when you create a block, right, like when you create this block here, right, and you say, hey, this is a statement of my block, this block is a statement of my block, and this return statement is a statement of my block. When you create the block, it will actually check, hey, are any of my inner statements blocks? If yes, it's just essentially pop that out. So yes, in real life, this will look like statement, 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 statement on the top level of the function. Yes.
Thanks.
Okay. Other questions?
So in JavaScript, JavaScript is much more lenient in terms of errors.
Mm-hmm.
So of course, in Java or Scala, like you can have an exception. but maybe you won't have the same thing if you implement the same kind of code in a naive fashion in JavaScript. So I wonder how, like, sometimes you will have a division by 0 or such kind of. I'm not very good at JavaScript, but I think sometimes you will have a division by 0 and it will return something else. I mean, for my, how I see things is often JavaScript accepts quite a lot of anything, but it's not really a good result.
Yes, yes.
So, so what would be, on the JVM, what would be an exception? Like not be an exception on the JavaScript side?
Yes.
And I wonder how do you handle these kind of things?
That's actually a very, very good point. There's a couple of things, notably null pointer exceptions, array out of bounds exceptions. Division by 0 is actually a very good example, which are obviously programmer errors. You shouldn't. The JVM is very nice because it throws you a nice exception and you can get the stack trace and whatnot. But it's a programmer error. That should not happen in the program. You should not divide by 0. You should check for that. Right? Essentially, it's.
You could do a try patch, worst case.
That's a very Pythonic way of doing that. I mean, I guess, without going into, let's say, arguments about how exception handling should be done in these cases, for the design of Scala.js, we considered every runtime exception essentially to be something that shouldn't happen, with the notable exception of number format exception, by the way. But so essentially, if you divide by 0, we consider this to be a programming error. Right? So we essentially have the choice to say, okay, JavaScript, if I just represent an integer by an integer, right, on the JavaScript VM, and I divide by 0, I probably get another number, which is not even an integer. Well, no, I'm actually going to get probably a double because it's essentially going to be positive infinity or negative infinity, even if I considered it to be an integer before. So what we do is we say, sorry, undefined behavior. Right? And a couple of these, you can actually decide whether you want us to throw undefined behavior error. I think casts are the best example. In Scala.js, casting to a type which is not correct, so essentially doing an instance of that fails, is undefined behavior, except if you specifically tell the linker, hey, I want this to be enabled. This is essentially for speed, because if we don't do that, we're extremely slow. Right? Yeah, go and look up the talk on semantics from Sebastian. Duan, I can give you the link to the talk, we can look it up. There's essentially a whole talk dedicated to why did we choose exactly which kind of things. And there's a couple of semantical tweaks, exactly because of that, because otherwise it's extremely hard to implement in JavaScript, and without a big use in our opinion.
First of all, thank you very much. This looks really cool. I've never used Scala.js before, but I have heard, this is hearsay, and I'd like to hear it from you. What are the, what should I expect in terms of either performance or emitted code size? Is this, I mean, it seems, based on the tagging and the traversal, it seems like you're explicitly sidestepping the pruning process, which is where a lot of optimizers kind of get hung up. Unless I do something kind of silly like accidentally call every single function in collections or something like that, it doesn't seem like it could emit a significant amount of code. But is this something that I should start using immediately for my entire site, or like is this something that is like I should do a significant amount of logic in Scala.js, or like is it that level of usability in your opinion?
Yeah, I mean, one thing you want to consider is just essentially going with Scala.js costs you, I'd say, about 200 kilobytes, right? Just for stuff that just goes in there.
Yeah.
Things like longs, just things we need is our runtime. Everything else grows as you go, right? If you include more, well, you get more code, but that's just fine, right? I mean, in terms of speed, I'd say this is competitive to handwritten JavaScript. So in benchmarks, we're sometimes faster and sometimes about 2 times slower, 2 to 3, but it's, I don't think we have a benchmark where we're like above 5 or 10x or something like that. There's benchmarks online if you want the details. But it's not like this is really going to run extremely slow. Performance is actually, thanks to the Scala semantics, it gives us a lot of static guarantees that the virtual machines internally optimize. This is actually pretty fast. Right?
That's cool. One follow-up, if that's okay.
Sure.
Is there an equivalent of like JS CDN or something like that? Because of the linker, it seems like everything gets inlined into one file. Is the effective Scala.js standard library able to be split out into something that can be hosted on a CDN for speed?
No.
Okay.
No, currently not. And let's say in the short to mid-term, we don't see how we can develop a story for that. Main reason is that the optimizer is too aggressive. Because the Scala standard library your project is going to use looks potentially different from the one that another project is going to use because it knows more stuff. As in, oh hey, this is actually theoretically polymorphic dispatch. But I know that in my whole program, I'm only instantiating this subclass. So this is monomorphic dispatch. So, inlining. However, if you combine that piece of code, which is completely elsewhere, with another piece of code that instantiates another subclass, boom. So it's, we have had discussions about splitting. People sometimes ask, hey, can I at least have a piece of code for my front end and a piece of code for my back end? I mean, as in the front end interface, front end login and for like the administration login, and a piece of common code. So I don't have to load these twice, but I also don't want to load the whole back-end administrative interface JavaScript code just for every front-end user, right? We don't have, yeah, something that is unsolved yet. There is approaches we did consider, but it's very hairy.
Thank you very much for your work.
Sure.
When you integrate Scala.js with, let's say, Angular, for example, or something else, and you want to call some function from in the Angular namespace, does it work the same like what you showed just before? You have something like an external call to, you had to alarm, for example, there I noticed.
Where is it? No? Sorry about that. This guy. No? Yeah, this guy.
Yes.
So essentially this guy, this is user code. You can write this yourself for whatever JavaScript library you want. Usually what people do is, I mean, there's also a completely dynamically typed interface, so you can just write dynamically typed code. Usually we don't recommend that, but we say, look, just write once the thing you need here, as you need it. So as you go, you essentially build up these, we call them facade types. And just on a neat basis, you just build these up. But this is user code. Everyone can write that.
Right.
All right. You can call this ang or whatever you need. You can rename that. Yeah.
So basically, the global scope that I say JS global scope just means outside of the area of this compilation, right? It means it's there somewhere and it's callable. So we just call it like this. It doesn't mean that you have a namespace there. That.
Well, this one actually means this is really the global scope, right? As you know, the alert method is not actually defining anything.
Yeah, that's what I said, because the alert is native, let's say, in the global scope. But how about?
You could call this, for example, object, I don't know, ang. I don't know, what's the Angular namespace? Ang? Yeah, right? Extends JS object. And then you would go, oh, okay, this is a value, a JavaScript value called ang, which itself is in the global scope. Right? And then you could just find these guys. It feels pretty natural. The same goes for classes. Right?
For example, one thing you would want to use is digest, for example, for the AngularJS that there is. So you would need to do something to the digest.
I'm not familiar with digest in AngularJS.
Okay, it's just that when you apply something to, when you want the changes to have a two-way as a binding, you want them to appear. Sometimes you have to explicitly let issue digest for it. Just an example.
Oh yeah, sure. You can essentially just define a method digest, and well, it says digest there. So without anything else from you, the compiler is just going to assume, okay, this method is also called digest in the JavaScript world. There you go.
Okay.
Other questions? Who's interested in the shame slide? So this essentially is things. Without these, the whole stuff I showed actually doesn't work. However, if I show all this stuff, this is not a 40-minute talk anymore. So maybe, who would like me to go over this? Maybe in 5 to 10 minutes. We have 10 minutes left. One person. Okay, good. Yeah, well. Would anyone like to do something else? Yes?
今、開発している、メインで開発している機能は何に注力していますか？次は何を開発しますか？
Right now, there's, let's say in the last couple of months, some very interesting features that came up were notably Scala-defined JavaScript classes. These guys up here. So you can essentially now in Scala say, hey, I'm defining this class, but this is not a class that has Scala semantics. This is a class that has JavaScript semantics. So that's very, very important, notably for UI frameworks, because they often rely that you can do that, and otherwise it's very, very unfluent, right? That's one thing. Then there's internal things. We added support for default methods recently. That's not really important from a Scala user-facing perspective, but it's important for the switch to 2.12, because the Scala compiler is going to assume that the backend supports default methods, and so if we don't, we have a problem and essentially need to either implement our own trait mixin or move them to the linker. No, we have to move them to the linker, because if we don't, we have a binary compatibility problem. Because essentially default methods, right, allow you for easier binary compatibility, and that essentially would mean if you have your Scala JVM code and your Scala.js code, they wouldn't have the same binary compatibility properties if we don't respect the default method specification, if you want so. So it's pretty important, but of course user-facing, nothing changes at all, right? So many things are actually like that. Other things that we're still looking into is better integration with JavaScript world thingies, module systems, whatnot. Yeah, but most of them are, for I'd say 98% of the usage, nothing's really going to change anymore. It's pretty much, right, there's rough edges. No, there's no rough edges. They're really just like details of like, oh, hey, but I'd like to do this and I can't. And I mean, of course, as the JavaScript standards evolve, right, ECMAScript 6 modules and stuff like that, they're in question how exactly is this going to work. But as for ECMAScript 5, yeah, we're kind of there. Sure. Okay, so let's look at this. Right. What are things I kind of omitted? One big thing is hijacked classes. One important thing if you work together with JavaScript is that JavaScript things remain JavaScript things, right? So if you have a string, right, well, you would want to be able to pass a string to JavaScript and get it back from JavaScript and get support for from the JavaScript virtual machine to use it and so on and so forth. However, in JavaScript, string is not even an object, it's a primitive value. So now suddenly the whole pipeline has to know that when you write Java long string, well, that's actually not a Java long string. That's not even a class. Maybe, right? And it becomes really funky if you look at things like car sequence. Car sequence is a super type of string. So if you have a car sequence, you might just have a normal car sequence there, somebody implemented. Or you might have a string, which is not a class, it's not an object in JavaScript string, so essentially the whole pipeline has to know that. This is what we call hijack classes. Primitive types are another example. We don't do any boxing in Scala.js. So a Java long integer is actually a JavaScript number, right? But the JavaScript number doesn't have a method double value, but Java long integer has. So if you call double value on a Java long number, you have to know, oh, this might actually be an integer under the hood. So I need to do all kinds of magic. That's what hijack classes are. As Scala.js defined JavaScript classes, they're essentially another class type so that the linker knows, hey, this class actually has JavaScript semantics, not Scala semantics, so you need to do a couple things differently. There's a couple of additional types in the intermediate representation, mostly to help string. Array types are just like on the JVM. And the record types are helper types we use internally. They don't exist in serialized files. We essentially use them for what is called scalar inlining. So for example, if you use a tuple in a local variable, we can potentially inline the two fields of that tuple. So you avoid an object application. Labeled blocks. JVM bytecode actually supports gotos. JavaScript doesn't. So we have to reconstruct a couple of things what the Scala Compiler generates and say, oh, this pattern is actually a pattern match, or this pattern is actually a tail call optimization. Therefore, I'm going to retranslate that back into a while loop. Oops. Hitting buttons. And modules, aka objects, as in when you write object something. The intermediate representation actually knows about these, and that's not the case for JVM bytecode. They're implemented as static fields. In the compiler special case is enumeration, because enumeration relies heavily on reflection internally, but we don't have any reflection. So without special casing that, essentially all of code would potentially break. So we have some magic in there. Reflective calls are difficult. I'm not going into detail function literals. There's some magic to translate function literals to generate JavaScript function literals. Export overloading. Right, so there's a whole system to actually detect, oh, hey, I have these 3 overloads, and how can I distinguish them? Because one of them has actually only 1 argument, so if I get 1 argument, I'm sure it's that overload. If I get 2 arguments, actually the second arguments are different in my overload, so I have to discriminate on this argument. Whatever. The linker. Something I've completely neglected is instance tests. Right? I said we erase interfaces, but we still need to be able to reply to the question, is this thing an instance of this interface? Right? So each object actually carries a dictionary of its supertypes, superclass types. Longs, JavaScript doesn't do longs, but so if you want longs, we essentially need to implement them with 2 integers. One is the higher part of the long and one is the lower part of the long, and do all kinds of bit twiddling to actually get the numbers out. Inheritance, how the actual inheritance works. In the piece of code I showed, there was just a constructor, but as is usual in JavaScript, every class has actually 2 constructors, one constructor that does actual work, another constructor that is inheritable. Further, we also have init methods, which is what you as a programmer would consider to be the constructor, but that's actually not the case even on the JVM. The constructor just allocates memory essentially and assigns the default values for each individual type of the fields. Semantics, we quickly touched on that, right? Undefined behaviors, also output modes. We can emit the ECMAScript 5, ECMAScript 6, we support ECMAScript 6 strong mode. These are essentially just linker flags, but of course in the linker there's all kinds of jazz to say like, oh, actually this thing here, I don't really need to synthesize this right now because I'm running on ECMAScript 6, so this is actually natively supported, and so on and so forth. There's synthetic methods. So these are methods that the linker generates as it loads the IR. Default methods are an example, right? Essentially the linker loads in default methods into the classes as it loads these classes. Yeah, it's more or less detail at this, let's say, overview. Further questions? Yes.
With all those transformations, can you debug produced code, or like how do you debug this when you write some Scala.js?
Very good question, very good question. Actually a problem that many JavaScript minifying frameworks have as well. So there exists this thing called source maps. Essentially it says, look, like this character in my JavaScript code maps to this line. We omit these. So essentially if you run Scala.js code in Chrome, and you pull up the debugging console, you'll see Scala code. Sometimes the stepping is a bit funky because one instruction might correspond to multiple ones, but you see your Scala code and it's very reasonable. All right, I think I'm just out of time. So this is pretty good timing, I guess. Thanks all for listening. And just hit me up if you have other questions.